Okay, so we are solving for question number 46. The highest possible energy of a photon in the emission spectrum of a hydrogen atom is, we have to find out. So, for the emission spectrum of a hydrogen atom, the formula that we mostly use is E naught 13.61 1 by Ni square minus 1 by Nf square Z square. Now, for Z for a hydrogen atom is equal to 1, so we will not consider Z square over here. So this is equal to EV, or the unit is EV rather. Now over here Ni equal to 1 and Nf is equal to infinity. That is indicating the maximum possible gap between two energy levels, and that corresponds to the highest possible energy of a photon in the emission spectrum of a hydrogen atom. So if we substitute the values over here, 13.61 1 by 1 square minus 1 by infinity square EV, the answer that we get is 13.61 electron volts. So let's solve the next question, question number 47. Standard reduction potentials of Fe3 plus going to Fe is dash volts. So basically this is going to be Fe3 plus 3 electron going to EV, and we have to find out the E naught value for this particular SRP. And we have been given what? Fe3 plus electron going to Fe2 plus is E naught equals to 0.77 voltage, and the other one is Fe2 plus 2 electron arrow Fe, and that would be E naught minus 0.44 voltage. Now, to get the first reaction, we have to simply add these two. Okay, so if we add these two, then we should be getting the above reaction, that is Fe3 plus 3 electron giving us Fe. Okay, so let's call this as E1, this to be the E2, and this to be the E naught 3, which we have to calculate. Okay, so the free energy for the following processes will be delta G naught 1 equals N1 Fe E naught 1, and this would be delta G naught 2 N2 F E naught 2, and for the third reaction it will be delta G naught 3 N3 F E naught 3, Just forgot the minus sign. Yeah. So now the principle that we are following over here, that the E are intensive properties, so they cannot be summed up, but the free energies are extensive property and they can be summed up. Okay. So basically what we are saying is that delta G naught 3 is equal to delta G naught 1 plus delta G naught 2. Now let's write them in the following format. And if we simplify further, then we can say it will be N3 E naught 3, N1 E naught 1, N2 E naught 2, or we can write this as to be E naught 3 is N1 E naught 1 plus N2 E naught 2 above N3. And so now if we plug in the values, N1 is 1 electron, okay, and that is going to be 1 times 0.77 volts plus N2 is 2 electrons, and that is going to be minus, that is E naught 2 is minus 0.44 volt divided by 3, and the answer that we will be getting is going to be around minus 0.036 volts. Okay, so that should be our answer. Question number 48 says the number of valence electrons in the complex Na2FeCO4. So Na2FeCO4 means we can write the complex anion as FeCO4 2 minus. So the oxidation state of iron, that is X, should be equal to minus 2, which means this is a D10 electron system. So for that we have 10 electrons. Carbonyl, there are 4 of it, and each carbonyl contributes 2 electrons. So the total will be 8 electrons. And so the system as a whole is a 18 electron system, and that should be our answer. In the Born-Haber cycle for the formation of CuCl, I repeat the question. In the Born-Haber cycle, the heat of formation of CuCl is, we have to find out. So let's draw the Born-Haber cycle, which is Cu solid plus half Cl2 gas, and that should be the heat of formation leading to the formation of, CuCl solid. Now, to us it is given heat of atomization, which I'm going to write as HAOTM. That means we get Cu gas. And then we have heat of atomization for Cl2. Let's write that too as HOTM prime. So we have Cl gas. And now the ionization energy should be written as only IE. Okay, that gives us Cu2 plus gas. And then we can write electron affinity, that is Ea. Okay, so that is Cl minus gas. And combining these two, we are going to have what we call the lattice energy U. Okay, so now if we add up all this, then we say delta HF should be H atom plus H prime atom plus IE plus EA plus U. And if we were to just plug in the values over here, that is 338 plus 746 plus 121 minus 349 minus 973. The answer that we get is 177. Okay, that also minus 177 kilojoule per mole. Okay, next question is 50, the spin only magnetic moment for the B2 molecule. Okay, so let us draw the molecular orbital diagram for B2. So this is the bonding anti-bonding for the 1s orbital, and that should be the 2s level, which are having the same bonding and anti-bonding. And let's fill up the electrons. So the corresponding bonding and anti-bonding electrons are these. Now in the 2p level, there is only one electron. Okay, so this is 2p, and we know systems like B2, C2 and N2, the degenerate pi orbitals are lower than the sigma 2p bonding orbitals. Okay, so obviously then we put the electrons, and in boron we have 10 electrons, that is in B2 we have 10 electrons in total. Let's call this as BAO, and this is B2 rather, MO. So this is the degenerate orbital. So now we are having two unpaired electrons in the pi bonding orbital. So now obviously we will have the formula mu B should be n plus 2 bm is going to be 2 plus 4, so that is 2 root 2, or we can say the value will be 2.82 mu b. Okay, so this is mu s. So the spin only magnetic moment of B2 is 2.82.